Welcome to the Deep Dive, where we take your stack of research and notes and distill it all down for you. Today, we are tackling, well, maybe the biggest topic there is, the profound improbability of you.
It's a fascinating tension, isn't it? On the one hand, you've got the stuff you're made of, the atoms, which are, almost immortal.
Right.
And on the other, you have this fantastically improbable chain of biological events that had to happen just right to assemble those atoms into you.
And when you look at life on a chemical level, the sources we've read call it curiously mundane. We're just made of the same atoms you'd find in a rock or, floating in space.
Exactly, but that assembly is so temporary. Even if you live a good long life, it's only about 650,000 hours. And after that, the atoms just silently disassemble and go on to be other things.
So we exist in this tiny window of luck, and we're going to explore that extraordinary string of biological good fortune today. Because, just surviving on this planet is hard. 99.99% of all species that have ever lived are gone.
Gone. So the big question for our dive is, how did we, in our very brief time here, figure all this out? The age of the Earth, its weight, what happens inside an exploding star.
How did we measure the impossible? That's what we're getting into.
And the place to start is right at the beginning, the Big Bang. Because it seems the universe is, finely tuned for us.
You mean those first ludicrously brief intervals right after it happened?
Yeah, fractions of a second old. That's when the fundamental forces, gravity, electromagnetism, all of them, they just sort of locked into place. And the numbers they locked in at, they had to be incredibly precise.
What would have happened if they weren't? What were the stakes?
Oh, total catastrophe. If gravity had been just a tiny bit stronger, the whole universe would have just collapsed back in on itself. Poof, gone.
And if it were weaker?
Nothing would have ever come together. No stars, no planets. Just a kind of thin, boring cosmic fog forever.
I saw a great example of this with the strong nuclear force. If you tweak its value by just a tiny, tiny fraction like 0.008%, all the hydrogen in the universe would have fused into other elements long ago.
And no hydrogen means no water, no fuel for stars. Game over. So yeah, it seems rigged. Which brings us to the next problem.
Our elements. The Big Bang only made the really light stuff, right?
Hydrogen, helium, a little lithium, that's it. But you're made of carbon, oxygen, nitrogen, iron, heavy stuff.
So, where did it all come from?
That's where the cosmologist Fred Hoyle comes in. A bit of a controversial genius, but he figured it out. He realized the only place hot and energetic enough to forge heavy elements was inside a star.
Not just any star, though.
An exploding star. A supernova. When a massive star collapses, the heat is just unimaginable, over 100 million degrees. That's enough to start fusing light atoms into all the heavier ones.
And then the explosion sprays those new elements, the building blocks of us, out into the cosmos.
We are, quite literally, stardust. It's an amazing thought. But Hoyle himself was a character.
I read he was embroiled in controversy for most of his life.
He was. He was right about nucleosynthesis, which is huge, but he also promoted some real nonsense. He claimed the famous Archaeopteryx fossil, the key link between dinosaurs and birds, was a total fake.
Seriously?
Oh yeah. Paleontologists were pulling their hair out for weeks.
Okay, so our atoms came from these violent, distant explosions. It makes you think about the scale of the universe. The maps of the solar system we saw in school are just so wrong.
And completely useless. They make it look like Pluto is the edge, but space is just so empty. The real edge of our solar system is the Oort cloud.
That's the giant shell of comets way, way out there.
Way out there. It would take you 10,000 years to get there. Pluto isn't even 1/50,000th of the way to the actual edge. That's our neighborhood.
And yet, through all that emptiness, the stuff we're made of is basically eternal. Atoms are described as fantastically durable. What does that even mean?
It means they last for about 10 to the power of 35 years. It's a meaningless number. But what it means for you is that every single atom in your body has been around for billions of years.
It's been through stars, through other creatures.
Millions of other organisms,
Yeah.
We're just temporary arrangements of immortal particles. The assembly is fleeting. The stuff is forever.
And the recycling is just mind-boggling. I saw an estimate that up to 1 billion of the atoms in your body right now were once in William Shakespeare.
And another billion from Buddha or Genghis Khan, anyone who's been gone for a while. It takes a few decades for the atoms to redistribute around the planet.
So not Elvis Presley then?
Not yet, no. His atoms are still making their way through the system.
That's an incredible thought. So we're made of this ancient, immortal stuff.
Yeah.
How did we, in our very short lives, ever figure out the rules of the game? let's get into the human side of this.
Right, because measuring the fundamentals of our own planet was a huge leap. It all really starts with Isaac Newton and his Principia.
Which was almost never published, right? Because he was in this huge fight with Robert Hooke over who came up with the inverse square law first.
Yeah, exactly. We have to thank Edmund Halley of Halley's Comet fame.
Yeah.
He basically badgered Newton into finishing it, and even paid for the publication out of his own pocket.
And that formula, $5 equals JMR22, it's one of those things everyone's seen, but the idea behind it changed everything.
It did. The idea that the force that makes an apple fall from a tree is the exact same force that holds the moon in orbit. That was revolutionary. It unified the heavens and the earth.
Okay, so that's the universal law. But then came the physical measurements, like what shape is the Earth exactly?
That fell to a French expedition to Peru in 1735. It was this massive, decade-long project to go measure a single degree of the meridian near the equator.
And they were actually hoping to prove Newton wrong, weren't they? They thought the Earth was sort of egg-shaped.
They did, but after nearly 10 years of unbelievable hardship in the Andes, they confirmed Newton was right. The Earth is an oblate spheroid. It's fatter at the equator.
Imagine spending a decade of your life just to prove your rival was correct.
That's the spirit of science, I suppose. And then, not long after, in 1797, we get The Weight of the Earth from Henry Cavendish.
Oh, this guy's story is amazing. A brilliant scientist who was pathologically shy.
Almost painfully so. He would only talk to his housekeeper through notes left on a table. One time, an admiring fan showed up to meet him, and Cavendish just bolted out the door and ran away down the street.
So how does someone that reclusive perform this huge, precise experiment?
He used a clever device designed by someone else, John Mitchell. It was a torsion balance. He measured the tiny gravitational pull between a big lead ball and a small one.
And from that tiny measurement, he could calculate the mass of the whole planet.
He could. Once he had the gravitational constant, g, he could plug it into Newton's formula and solve for the mass of the Earth. And his result was only 1% off what we know today. Just incredible.
So by the end of the 1700s, we knew the shape and weight of the Earth, but the age was still a total mystery.
And a source of fierce debate. Early on, a French count named de Buffon got in trouble with the church for suggesting the Earth was maybe 75,000 years old. He based that on cooling iron balls.
Which was a wild guess, but radical for the time. But the real fight came later, with Lord Kelvin.
Right. In the late 1800s, Kelvin, who was maybe the most famous scientist of his day, insisted the Earth could be no older than 20 million years.
And that drove geologists and biologists crazy. Darwin knew evolution needed way more time than that.
It was a huge roadblock. Physics seemed to be saying that natural history was impossible. The breakthrough came from a completely new field, radioactivity.
Ernest Rutherford and Frederick Soddy.
They made two huge discoveries. First, radioactive decay gives off heat, a lot of it. That's the engine keeping the Earth's core hot, which meant Kelvin's cooling calculations were wrong.
And the second discovery?
That the decay happens at a perfectly steady, predictable rate. It's a clock, a natural clock built into the rocks themselves.
And the sources say this was literally alchemy, pure and simple, turning one element like uranium into another, lead.
It was. And that led to the final chapter in this story, Claire Patterson. His job was to use this new clock to finally date the Earth.
But he ran into a massive problem.
A wilderness of contamination. All his samples were contaminated with huge amounts of lead. At first he thought it was his lab, his equipment.
But it wasn't.
It was the entire planet. He traced it back to one man, Thomas Midgley Jr., the engineer who invented leaded gasoline, and later, CFCs.
Wow, that guy had a real knack for planetary scale disasters.
He really did.
Yep.
So Patterson had to find a pristine sample, something that was formed with the Earth but hadn't been polluted by us.
Meteorites.
Exactly. Chunks of rock from the formation of the solar system.
Mm-hmm.
He also developed the science of using ice cores to look back at atmospheric composition, which is the foundation of modern climate science.
And he got the number.
He did. In 1953, he announced the age of the Earth was 4.5 billion years old. But he didn't stop. He spent the rest of his life campaigning to get lead out of gasoline.
And he won. The ban in 1986 caused lead levels in the blood of Americans to drop by 80% almost overnight. A real hero.
A true scientific hero.
It's an amazing story of human ingenuity, but it all rests on this incredibly long, fragile chain of life. So let's pivot to that now. The tenuousness of life and extinction.
And just like the history of science, the history of paleontology is messy.
Yeah.
It was driven by these huge, dramatic rivalries.
It's like the story of Gideon Mantell. He discovered the iguanodon, but he was just persecuted by this guy, Richard Owen.
Owen was a powerful and apparently very cold character. He was anti-Darwin, and he just systematically tried to erase Mantell's contributions, even renaming his dinosaurs.
The end of Mantell's story is just tragic. He had a carriage accident, was left in constant pain, and eventually took his own life.
And to add one last cruel twist, Owen, as the director of a major museum, ended up with Mantell's deformed spine in his collection.
That is just brutal. And you see the same kind of drama in the American Bone Wars between Marsh and Cope.
Oh yeah, Marsh had all the money from his rich uncle George Peabody. Cope was the more productive scientist, published 1,400 papers, but he died broke in a single room.
It seems like the biggest drama, though, was over what actually killed the dinosaurs.
For sure. For decades, the absolute consensus, the scientific religion, as one source puts it, was that extinction was slow and gradual. The idea of a sudden catastrophe was just heresy.
Until Walter and Luis Alvarez found that layer of iridium all over the world.
Iridium, super rare on Earth, but very common in asteroids. So they proposed that a 6-mile-wide asteroid hit the planet. And the paleontology community, well, they hated it.
I read that Luis Alvarez called paleontologists stamp collectors.
He did. He had a lot of contempt for them, but the evidence was just too strong.
The scale of that impact is, I can't even picture it, the force of 100 million megatons.
It would have thrown so much dust and debris into the atmosphere that it just blocked out the sun. For months, maybe years, a global winter overnight.
So the question is, what survived and why? Our ancestors, these small nocturnal mammals, they did great.
They were perfectly suited for a dark, cold world. But here's the mystery. Why did things like crocodiles and toads and newts, seemingly delicate creatures, make it through just fine when every single dinosaur died?
That's still a big question mark.
A huge one. It just highlights how much luck was involved. We are here because of this extraordinary string of biological good fortune. And it can all vanish so quickly. Just look at the dodo.
Right. Wiped out in just 70 years after we first met it. We don't even have a single complete skeleton or an egg. It's just gone.
It's the perfect tragic reminder of how fragile this all is.
Which brings us back to where we started, this idea that Earth seems so perfect for us.
And we have to remember it feels that way because we evolved to fit its conditions, not the other way around. It's a logical trap.
Richard Feynman had a great joke about this, didn't he?
He did. He'd say, "You won't believe what happened to me. I saw a license plate that said ARW35E7. What are the chances of me seeing that specific plate tonight?"
Of course the odds are 1 because you just saw it. It only seems improbable in hindsight.
Exactly. And that brings us to the final thought for you to chew on. Think about your own ancestors. Go back just 64 generations.
Okay, to about the time of the Romans.
Right. The number of individual ancestors you have in that generation, each one a slot in your family tree that had to be filled, is over 1 billion. That's a 1 with 18 zeros.
Wait, that's thousands of times more people than have ever lived.
It is. Of course, the number shrinks because of overlapping ancestors. But the point is about the chain. A perfectly unbroken, specific line of couplings had to happen without a single failure stretching all the way back.
So on one hand, you share your atoms with Shakespeare and Buddha through this constant, massive planetary recycling. The matter is permanent. But you're only here because of a specific, fragile biological line that had to succeed at every single one of those billions of opportunities. What does that tension between the immortal stuff you're made of and the breathtakingly fragile life it creates mean to you?